And good morning, afternoon, evening, whenever you're watching this. All right, going through a little bit more stuff about electricity. Today is going to be with series and parallel circuits, and we want to be able to differentiate them, be able to look at a diagram and understand which one's which, talk about the advantages, disadvantages, what happens to uh, voltage, current, resistance as we add and remove things to it, and start touching on how to do a little bit of math with this stuff. So we're going to say what are circuits, specifically then what is a series circuit, what's a parallel circuit, how do we apply Ohm's law to each one, and that largely is our vocabulary with series and parallel circuits. So off we go. Um, what is a circuit? You probably know this already. We've been working with them in class. Effectively, it's just a complete pathway that electricity can travel through. A couple of the diagrams you have on here, even with a direct current showing on here, there is you need an electricity source, and you basically, if it's working, you've got something in it that's a resistor, like a light bulb or a refrigerator or whatever it might be, that's going to be using that current. Technically, you don't need a resistor in a circuit. You could hook a wire up and just run it around, but there's no real purpose in doing that. But as long as we give the electricity a pathway to flow, we effectively have a circuit. And most of what we're going to be looking at today is kind of more of a direct current circuit, the way the diagrams will be looking and so forth. So that's kind of what you're going to see. There's two different basic types of circuits that we can classify things into. There's a series circuit. Series is one after another one, such as why it's named. There's really only one pathway that the electricity can flow through. And you'll kind of differentiate this in a minute. Hopefully, it makes sense. You can look at the diagram. The diagram that you see here is a series circuit. This symbol over here on the left is your voltage source. So this is the battery, and the arrows are giving us an idea about the direction that the electricity is moving. These little zigzaggy things are standing for our resistors. So this could be a light bulb or a curling iron or whatever it is that's using the electricity. There's three of them in this circuit, so that they're noted as R1, R2, and R3. So we got three different resistors, just numbered that way. The other numbers on here would just be useful if we were trying to talk about how much current or voltage is there at 0.1, 0.2, 0.3, 0.4. So they don't necessarily mean anything. They're just there for reference. The math for Ohm's law works as we've been doing before. The voltage is current times resistance. Again, the I is used for current, comes from the French word for intensity, because that kind of tells us a little bit about the current. Think about a bulb. The brighter it is, it's due to the intensity of the current. So that's why we don't use a C. Americans don't ever do everything first, so sometimes other languages get to name things. All right, so if we do some math with, excuse me, got the cough this morning, with Ohm's law, we're basically just using V equals I times R. And so if we take screenshots over here from simulation, so if this is a 9-volt battery, it's red, so you can see a little bit better. This is a 9-volt battery. And I think each of these bulbs was supposed to be 10 ohms. So in a series circuit, if we've got more than one thing, we basically just add them together. If we know that our voltage is 9 and we've got two resistors in a series circuit, we're just going to add them together. So our total resistance is 20. And if we wanted to figure out what's the current, when we go through all that, again, I'm solving for I. So move the R to the other side, and V over R equals I. So in this case, we'd have 9 over 20 equals I, and that's going to come out to be about 0.45. And again, this would be in terms of amps, so since we're doing a current. Right. We had 4 bulbs in a row. We would think about it the same way. Again, each of these is 10, so we would end up adding all of that up. So obviously it would double. The resistance now would, instead of be 20, the resistance would be 40. We do the math the same way, except now we do 9 divided by 40, and then that number is going to end up being half of what it was, which is going to be 0.22 amps. And you can see that this number is half as big as this number. So if you double the resistance, the current's going to proportionally go down, and that's how we get the math on that. So if we had more than one battery, we would simply add the voltages of the battery. If we have more than one resistor, we simply add the voltages of all the resistors together. The current is going to be the same throughout it, no matter where we take it. And so we don't have to worry about the current changing wherever we go. So these are used in very simple things. In a flashlight, for example, complicated things generally don't use something like this, because one of the key disadvantages of this is if one bulb goes out, then they all go out because the connection is broken. And so if you had a series of resistors that were all using the electricity, they all have to be working for the whole thing to work. So you can think about the way your lights in your house work. This is generally not how it's going to be wired up, because in your house, you don't have to turn everything on for everything to work. We can turn one thing on, we can turn one thing off. So this is not how most of the things around us are wired. This is how a lot of simple things might be wired. If there's usually often just maybe one use of something, one kind of resistor on the circuit. A parallel circuit is more complicated. You can see the diagram down here in the bottom. It's still a complete pathway for electricity. But what we see is that there are multiple pathways that the electricity can flow through. We still have a battery over here on the left. And as the electricity flows, once it gets to point 2, notice the electricity's got, let's see, options here, because it's electricity, doesn't really have options, but it will flow either to point 3 or it will flow to point 7. Some of it will go to 3 and some of it will go to 7. Once it gets to 3, some of it will go to 4, some of it will go to 6. And at this point, at 4, it doesn't really have any choice. It's got to go to 5, and it's going to make its way back around to the side of the battery where it's got the lowest voltage to get back to completing the path, right? So because we've got multiple resistors, the math gets a little bit more complicated, because if each resistor is different, then each current in each of these paths are a little bit different. And that also makes the current in these areas a little bit different as well. So the voltage in this battery is going to stay the same, or this circuit voltage is going to stay the same. But if the resistors are different, then we're going to have different amounts of current going through each of the branches, and we're going to have a different amount of current at the parts that aren't involving the resistor. So the math looks a little more complicated. All right, so here's the rules for parallel. The total voltage in the circuit is the same no matter where you're at. Thank goodness, it makes it nice and easy. The total current that we have, particularly what we're talking about, like probably here, the total current like we would have here and here before it gets to the resistors is going to be the current added together through each of the branches. And we'll see how this works in a minute. The total resistance is mathematically even weirder. We have to take the reciprocal and then add all those together. Fortunately, there's ways to solve this that aren't quite as complicated, but we'll probably go through all of this. So I'm going to go through an example problem now. Following up to this, you're going to be given some more general math problems to do with this. Probably not today. It's not going to be a math day situation, but I'm going to go ahead and touch on it because you're going to need to be able to do this in all likelihood tomorrow. So I kind of want to go through and show how to do this. So that should say, what if we had a 12-volt battery in this situation and our resistance was as such? And this one, you're going to end up writing out a bunch of stuff to kind of keep track of everything. So we're going to draw, if I've got a 12-volt battery here and my resistance, this is 5 ohms, and this is 10 ohms, and this is 12 ohms. Okay. We kind of want to end up making a chart for all of this because we've got and we have to use little sub thingies down here to kind of keep it together. So we've got the total resistance, we've got the total current, and we've got the total voltage. And so we also need to do the same thing for each branch. So I'm going to write all these things down too. So I've got an R1. And again, if you're taking notes, you should probably be writing all this down because you're going to be tasked with doing this eventually. All right. Again, T's for total, 1, 2, and 3 are for each of the different branches that we have. So let's go through and note what's given to us in the problem. Again, so we've got a 12-volt battery, and then our resistance is 5, 10, and 12. What we want to do is make sure we fill in the rest of these blanks. Okay, so let's start with this. Here's the easy part. Voltage is going to be the same throughout, no matter where this is a 12-volt battery or 12-volt circuit. So we can go ahead and fill in the blanks down here. Now, the other part is that in each branch, Ohm's law still applies. And so we're going to treat each of these as a series circuit, basically, when we do the math. So for R1, R2, and R3, we're only missing one spot here. So this should be pretty easy for us to answer. So how do we get that number? Again, I'm going to need to rearrange my formula. So it's V over R equals I. So if I do 12 over 5, I'm going to get this number. We got 2.4. It's supposed to be a 4. Right. How do I get this number? V divided by R, 12 divided by 10. So it's going to be 1.2. And how do I get this? Third resistance, current, voltage divided by resistance, 12 over 12, and that's going to be 1. We got 2 boxes up here to be able to get. Now notice how do we get the total current? We add up all of the other currents. All right, well, that makes it easy. So we got all these currents. If we just add those up, again, 2.4 plus 1.2 plus 1, that's going to give me, add them all up, that should give me 4.6. Double check my math. Yep. And then we're missing this piece over here now. And how do we get R? All right, put I on both sides. So to get R, I need to do V over I, which is going to be 12 divided by 4.6. And when I do that math, I'm going to get about 2.6. But what you'll notice is kind of some oddities going on is that current here, the current in these places, which is that number, is larger than the current in each of the branches that we have right here. And so effectively adding additional branches raises the overall current and actually starts making these things brighter and brighter and brighter because it contributes to more and more current. So we'll probably look at some examples of this, put some things together with some batteries and bulbs in class to kind of go over it. But this is the basis of math that we're going to be working on, math that we're going to be solving. And again, we're going to use these rules to be able to do so. Right, so let me clear this off. Let's see if we can get this wrapped up. All right, so if we compare what we've got on these pictures up here, these top two, we've already seen pictures of those. Those are our series circuit. You'll notice I put the ammeter on here. This one's got a current of 0.45. This one's got a current of 0.22, which is approximately half of what these are, because again, there's 2 more bulbs. So the current gets cut in half. We'll go down to the bottom. These are parallel circuits. They're all the same one. I just made different pictures so that I can move the ammeter around. You'll notice when I stick the ammeter here, it's 0.45. When I stick the ammeter up here, it's also 0.45. But when I stick the ammeter here, it's actually 0.9, which is those 2 numbers added together. And again, that's kind of what the rule is for these. The voltage would be the same all the way throughout. The resistance for each of these 2 branches would be the same, which is why the current ends up being the same. But the current gets added up right here. And you'll notice that these 4 lights are way brighter than these 4 lights because of the way that they end up being wired together. Actually, these 4 lights are just as bright as these 2 lights. So the amount of current going through these 2 lights is the same as the amount of current going through each of those 2, but they end up getting doubled in the rest of the circuit. All right. So again, the circuit's a complete path. Series has one pathway, parallel has multiple. The math of Ohm's law, V equals IR, applies to each, but is slightly different. And again, we went over that vocabulary. Thanks for joining me. We'll see you again later.